Hello and welcome back. This is lesson 9.4 about parallel lines and proportional parts. We have two main theorems today, or at least a theorem and its converse. Theorem 9.5 and 9.6. Theorem 9.5, the triangle proportionality theorem, states that if a line is parallel to one side of a triangle and intersects the other two sides in two distinct points, then it separates these sides into segments of proportional lengths. So in this example, we have, here's the line that's parallel to the side of another triangle. So we have HD is parallel to the side of the triangle IL. And it intersects the other two sides of the triangle. So it intersects here at H, here at D, in two distinct points. And if this is the case, it separates these sides into segments of proportional length. So we're looking at these segments SH, HI, and SD and DL. So if the line segment HD is parallel to segment IL, then SH, so this segment SH, right here, divided by IH, or HI, this segment, that ratio is the same as dividing SD by DL. So that is the triangle proportionality theorem. So a parallel line, in other words, a parallel line cut through a triangle like that is going to make these segments proportional. I thought it might be interesting to see why that is, so a little bit of a proof of this theorem. So here's our diagram. If HD is parallel to IL, we have a triangle that would be kind of a smaller triangle, SHD. And we have the bigger triangle, a bigger triangle, ISL. And there's a point here that's an H, and there's a point over here that's a D. Not drawn to scale very well, but hopefully you get the idea. You have the small triangle and the big triangle. They share this angle S. And the key is if the segment HD is parallel to IL, then by corresponding angles, these angles are congruent angles. So in the big triangle, it's angle I is congruent to angle H in the small triangle. And then we have angle-angle similarity. And if we have angle-angle similarity, then the sides are proportional. The corresponding sides are proportional. So that would mean that this side, SD, is in some relationship, some ratio with this entire side. And that ratio would be the same as this side SH divided by this side SI. So we could write a proportion like that. I'll start with a big triangle. We could say that the side SL divided by, so that's this big side, divided by SD, that would be equal to SI divided by SH. If you want to take notes on that, that's great. I'm doing it on a separate page because I didn't really have enough space over here. I don't know if it would really fit over here or over here, but it's up to you. You could always take a separate piece of paper out. So since we have angle-angle similarity, we can say that the sides are proportional. That's not exactly, though, what the theorem states. We can take this SL here, SL, and by the segment addition postulate, we can break it down into SD plus DL, SD plus DL, divided by SD. And then this SI side, we can break it down into its segment addition postulate, SH plus HI. over SH. So kind of first showed they were similar, next wrote the proportion based on their similarity, and then third used the segment addition postulate. And notice we have in this first fraction SD, so we have SD divided by SD plus DL divided by SD. And we can write this as two separate fractions, SH over SH plus HI over SH. That's kind of my fourth step. Not really doing a two-column proof, just wanted to show you where the formula comes from. And SD over SD, this is a 1. And SH over SH, anything divided by itself, is a 1. So we could subtract 1 from both sides. And we're left with DL equals that. So let me write that over here. DL over SD equals HI over SH. And what that gives us here is the triangle proportionality theorem that SD and DL, so if you take this side length divided by this side length, that's in the same ratio as this side divided by this side. And that's the triangle proportionality theorem that we have right there. The converse of the triangle proportionality theorem is if a line intersects two sides of a triangle. So here we have a line intersecting two sides of a triangle. Separates the sides into corresponding segments of proportional widths. So if this ratio equals this ratio of lengths, then this line must be parallel to that third side, the side that was not intersected. So we would say if, for instance, this length AB divided by BC, that side, that equals DE over CD. If that's true, you have proportional lengths. That's what those two fractions equaling each other is telling us. We have proportional length segments. Then it must be that BD is parallel to AE. And that's the converse. You might remember a converse, you just switch the hypothesis and the conclusion of a theorem. So the converse is just switching these two. And let's use this theorem and its converse to answer some questions. In this triangle, we're told RT is parallel to VU. So we should mark the diagram. SV is 3. VR is 8. UT is 12. Find SU. I'll call that X. So with the triangle proportionality theorem, the sides that were created by these parallel lines, these segments, we can write a proportional relationship. So we could say 3 over 8 equals X over 12. And at the beginning of the chapter, we learned how to solve proportions like this. We cross multiply. 3 times 12 is 36. 8 times x is 8x. And we divide both sides by 8. Uh, 8 goes into 36 4 times 4 4/8, I believe. So that would be 4.5. Would be the length SU. Let's try to set up another proportion and see if it works the same. This time I went this way and compared. Would it work if we did 3 over x equals 8 over 12? Notice when we cross multiply, we do get the same 8x equals 36. That's pretty nice relationship. As long as you're consistent, I don't think it'll work if you try to do 3 over 8 equals 12 over x. 3 over 8 equals 12 over x. That's not being consistent. If you're going to start with this smaller one and go to the left, you have to start with this one and go to the left. This would not work. In the next example, we're given the length DH is 18, HE is 36, and DG is half of GF. So let's just call GF a length of GF, that's G to F, GF. DG is half of that, so D to G is going to be 1/2 of GF. And the question is, determine that these two segments are parallel. When you're determining the segments are parallel, then we're going to be using the idea of the converse of the triangle proportionality theorem. So we need to show that the segments that are formed are proportional to be able to prove that the lines are parallel. So let's write a proportional statement. Let's do 18 divided by 36. Does that equal, is it the same proportion as this 1/2 GF divided by this one, GF? There's some reducing. We can do 18 over 36 is 1/2, and GF divides by GF. It's the same length, so it divides out. So we'd say, since the segments formed are proportional, GH is parallel to FE by the converse of the triangle proportionality theorem. As they asked us to explain, there's an explanation. I do want to point out about these theorems, to be really careful, the theorem doesn't tell you anything about the relationship between the length of HD and the length of IL. Notice that we could very well draw HD up here instead, and that would still be parallel to this side. You're going to have a proportional relationship between these segments, those segments. However, this length now that I have right here is much longer than this one. And also, notice when we're comparing these segments, this segment SH is the side of a triangle, whereas this segment HI is not the side of a triangle. It's only part of the side. So if you wanted to try to compare this side, which is the side of a triangle, with this entire side, you'll have to figure out another way to compare them, but they're not necessarily in a proportional relationship, matching these proportions that we had in this theorem. So be really careful when you're, if you're asked to find those lengths. Let's look at the second page. I'd encourage you to pause the video and see if you and your neighbor can figure out these 4 questions. Whenever you play the video, we'll walk through them together. So first, on A, if you pause the video, I hope you did, are the triangles similar You would say yes by angle-angle similarity. We have these angles are both 90-degree angles. And the large triangle and the smaller triangle both share this angle. We'll call it angle A. So they are similar triangles. If you wanted to use the triangle proportionality theorem, you would need to set up a ratio of 30/60 equals this length divided by this length. But that's not exactly what you're asked for here. This is actually what I was just warning you about a minute ago. These sides those sides are not talked about in the triangle proportionality theorem that we saw on the first page. Only these sides are. So what we need to do is just write a proportional statement, let's say 60 over 100. 60 over 100. What side is corresponding to this 60 side? Well, that would be this entire side, which is 90. And then the distance we're looking for. And when we cross multiply, we get 60 times d equals 9,000. D equals 9,000 divided by 60, which 6 goes into 9 once, 30. I believe that would be 150 feet is the distance across the lake. That's a pretty cool way to find a distance across something that you might not otherwise be able to find a distance across. Just getting a measurement here on dry ground seems easy enough, and then getting two other measurements. You'd have to make sure that you have similar triangles like these. On this next one, we're told that all these streets are parallel, and we'd like to find the value of x. The thing to notice inside here is that you have a triangle, and you're told that these are parallel sides, so you can use the triangle proportionality theorem. We could say 26 over 13 would equal x over 16. So that looks like double. It looks like x is going to be 32. And I guess the units are blocks. 32 blocks. Find the values of x and y. Notice that two segments are marked as congruent. So maybe we'll start there. These two segments are marked as congruent. So 2x plus 2 must equal 3x minus 4. Subtract 2x from both sides, add 4, so x is 6. If x is 6, then this length is 14, and this length is also 14. These segments are not marked as congruent, but we can use the triangle proportionality theorem since we have a triangle here. We can state 14 over 14 would equal 8/3 y plus 7 over 5y. Cross multiplying, divide those out. Turns out that those two segments are congruent after all. I'm going to multiply both sides by 3 to get rid of the fraction. We get 15y equals 8y plus 3 times 7, 21. Subtract 8. That will give us 7y equals 21, so it looks like y is 3. And x is 6. And then lastly, we have similar triangles here. these two angles would be congruent, and the 90 degree would be congruent. So we could just set up a proportion. This isn't really the triangle proportionality theorem, but we could say 6 over 1.5 must equal the unknown x over 7. And we're told here that they are similar by angle-angle similarity. So you can cross-multiply and solve for x, and that would be how tall the flagpole is. Thanks for watching this video. See you next time.